All right, secondary educators, let's take a look at something we're supposed to know how to do, and that's fairly foundational to what we do with quadratics. Let's take a look at completing the square and how it's done and how we use it. Let's do this. We're going to describe y equals x squared minus 8x plus 18 as the image of y equals x squared after a sequence of transformations. You may want to pause the video and give it a go to make sure that you remember how to do this. Okay, so I'll give it a go. So what do we have? We have y equals x squared minus 8x plus 18. And what are we trying to do? We're going to try to rewrite part of this as a perfect square trinomial. We want this to be a perfect square trinomial so that in the next step we can write it as blah 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 squared. So how do we do that? Well, we write the x squared minus 8x here, and we write the 18 there. To make this a perfect square, this is going to be x minus something. What's that something? Well, that something is going to be half of this, right? Because when we expand the brackets here, when we multiply these binomials back together, we're going to get a one of these and a one of those, and they're the same, and they add up to negative 8x. So this has got to be half of that b coefficient right there. But you and I both know that x minus 4 squared is x squared minus 8x plus 16. 16 is the number that completes the square. But you can't just add 16. That breaks every rule of math. So we don't add 16. We add 0. And when we add 0, that doesn't change the value of what we had in the line before. So this part is plus 2. And so now we have a complete square form of the original question of the parabola in the question, but now we know what's happened. We know that this parabola is the image of y equals x squared after a translation. Well, what translation? Well, this moves 4 to the right, and that moves 2 up. It moves 4 to the right and 2 up. Well, we could do it again. We could describe this parabola as the image of y equals x squared after a sequence of transformations. We can do that. It gets a little tricky because we'd like to pull out the negative 2, wouldn't we? This is x squared plus 6x plus some number minus a 7/2 minus some number, right? Because we want this to be negative 2 times something squared and then some number back here. So to make this happen, this part has to be a perfect square trinomial. Well, what perfect square trinomial is this going to be? Well, this 6 tells me that we're going to have an x plus 3 here, so that when we square that x plus 3, we're going to get a 3x and another 3x. That's 6x. That's this 6x. But again, you and I both know that x plus 3 squared is x squared plus 6x plus 9. 9 is the number that completes the square. So we add negative 9 within these same parentheses so that we can change the appearance without changing the value. Hashtag INTD302. So then what happens? Well, this part's easy. This is the x plus 3 squared. This part's a little more difficult. That's negative 7/2 minus 18/2. That's negative 25/2. This part is negative 25/2, but it is being multiplied by negative 2 on the on the distribution that's happening here, and negative 2 times negative 25/2 is positive 25. This is the parabola in complete square form. So this parabola is the image of y equals x squared after, well, 3 things happen. what are the three things that happen? There's a dilation vertically by a factor of 2, and then there's a reflection over the x-axis, and then it's translated 3 to the left, 25 up, right? It's translated 3 to the left, 25 up. So it's a vertical dilation of factor 2 centered at the origin, then a reflection in the x-axis, and then a translation along negative 325. But wait, there's more. It's not just about parabolas in complete square form. You can solve using completing the square. And to solve using completing the square, well, that's not too bad. We just make sure that the constant moves to that side because it's easier to complete the square. In fact, it's easier to complete the square if this lead coefficient is a 1, so we're going to make the lead coefficient 1. And then we're going to ask ourselves, what's the number that completes the square? 2 lines down, we're going to want to say x plus something squared is a number. Well, what's that going to be? Well, that's going to be half of this 3, because we're going to get a 3 halves x and a 3 halves x, and they're going to add to this 3x. But you and I both know that when we expand this, we get x squared plus 3x plus 9/4. And so sure enough, 9/4 is the number that completes the square. But we can't just add 9/4 to one side of the equation. We add 9/4 to both sides of the equation. And middle school math tells me that that's 71/12. So then there are 2 roots. How do we find the 2 roots? Well, x plus 3 halves is plus or minus the square root of 71/12, which algebra 2 teaches me is the square root of 213/6. So what's x? Well, x is, kick that over, negative 3 halves plus or minus the square root of 213/6. And some people are going to insist on getting a common denominator, and these people are fine mathematicians also. I would argue that either of those are in simplest form. I would argue that either of those is an exact answer in simplest form. And so now we can see that we can use completing the square not just for putting parabolas in complete square form, but also for solving quadratic equations. I hope this is a good refresher for those who need it, and we'll see you in class.